Hi, let's discuss hypothesis testing. This is also known as statistical hypothesis testing. A typical experimental situation is that we want to study a population. The way we do so is often through a sample. That is, we randomly select a couple of individuals from the population and we concern this as our sample. The saying is that we observe the population through a selected sample. And in the process, we subsequently measure our measurements on the individuals in the sample. In the process, we're subjecting ourselves to sampling errors. That is, the selection process itself contains errors. We are not for sure to be able to cover exactly the variation of the original population. We as well subject ourselves to measurement errors. That is, when we do our measurements on the individuals, we are introducing errors. These can both be systematic, that is also known as biases, or they could be in the form of noise, measurement noise, that is random fluctuations. There's as well another layer of problematics here. For the individuals, we can have biological variation, but there's as well this technical variation in the measurement process. Okay. Often, particularly in biological research, we are not so interested in observing one single population as such. We often want to contrast one population to another. So this could typically be that we want to make an assessment about differences between healthy and diseased individuals. So the way we do so is that we pick random samples both from the healthy population and diseased population, obtaining now random sample for them both. We can then form statistics from this, i.e. or e.g. the observed mean of the individuals. So when we do our measurements, we assess the individual measurement from each individual, and then we form a mean from this. The statistic itself is not good enough to make an inference from, because we know that there will always be a small difference between whatever sample we make, or there will always be a difference between the observed means of two different samples. Instead, we are wanted to make a statistical model of the difference between these. So what would be reasonable to observe a chance between the difference between the observed means of the two samples? And the goal of this is to make finally an inference, that is a conclusion regarding the difference between these two populations. So we're studying the sample. We're making samples in order to study the populations, and our final inferences should be a conclusion regarding of the populations. So in order to do this procedure, we need a couple of helpers. The first ones being the hypothesis that we put up. So a hypothesis is a statement about a population parameter, and that could typically be something regarding the means of our populations. And the first one, most important hypothesis we put up is the null hypothesis. That is typically the situation we're not interested in. So, for instance, we could assess that there's actually no difference between the healthy and diseased populations regarding the statistic we are interested in. We as well sometimes make what we call an alternative hypothesis, and that might be more in line with the situation we want to detect, i.e. that there's a difference between the healthy and disease. The role of these hypotheses might not be obvious at first. Particularly null hypothesis is interesting. The reason why we make the null hypothesis in the first place is actually that we want to disprove it. So we are looking on the differences in the sample means, and then we'll want to say that actually the difference in sample means that we observe is so extreme that it's very unlikely that this will occur just by chance. So hence, let's reject the null hypothesis. The next helping thing we have is our sampling distribution. That is a sampling distribution that's distribution of any statistic of measurements in a sample. In our case, it could be the mean. And if we know the sampling distribution of the difference between in a sample mean under the null hypothesis, we can calculate how extreme this difference is. The actual parameter that we assess from the sampling distribution is a p-value. So that's the probability of how extreme this current situation is. So the probability of observing a result that's least as extreme as the one that was observed under the null hypothesis. This is known as a one-sided p-value. If we instead look on the absolute value of the observed situation, we can assess as well what we know as a two-sided p-value. That is how extreme is it that you either as large or as small as the current situation. That's the current difference between means. A property that we will use later on is that when we do our multiple hypothesis correction, is that the p-values themselves by definition are uniformly distributed under the null hypothesis. That is, if the null hypothesis is true, we are as equally likely to observe a p-value of 0.1 as 0.3 as 0.9. Okay, so if we repeat this statistical inference procedure, we are interested in determine a difference between the healthy and the diseased population. So the way we do so is by collecting random samples from both the healthy and diseased population. This is known as a sample. We'll then look on the difference between statistics of these samples, typically the mean, and we can build up a statistical model of the properties of the difference in the means. We then make an inference, a conclusion regarding the difference in the population. So we actually, by placing ourselves in a situation where we say that there's actually no difference whatsoever between the healthy and diseased population, we want to sort of assess how likely is it that we observed a difference as large as the current one. And the way we actually do this in the end is that we, if we find the observed differences in observed means as being very extremely low, then it means that there's actually very little reason to believe that the null hypothesis is true, and then we reject the null hypothesis, and we actually make the conclusion that there is a difference between the healthy and diseased population.